The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
So our next speaker is Ken Bondi, and to some degree he may not need an introduction. He's been a part of ACI here for many, many years, but he's going to speak on seismic retrofit using externally bonded post-tensioning. Ken is a licensed structural engineer. He's been involved in post-tensioning and repair of concrete structures for almost 50 years. Extremely active in ACI and PTI. And I will also say that if you're a contractor like I am and you goof up some post-tensioning, he's not a bad guy to call because he can hopefully bail you out of problems that you create on your own. So with that, I'm going to introduce Ken.
Thank you, Pete. I think I deny some of that. But the use of externally applied post-tensioning tendons is a very powerful method for the strengthening and repair of existing structures. It's been used in all types of framing and all types of structural materials. It's been used to repair concrete buildings, structural steel buildings, and wood structures, a lot of wood structures. It's a unique method in that it increases the strength of the existing structure and it physically reduces deflection in the existing structure. In the 23 years that my design and construction companies, my Seneca companies, were active, and that would be from the mid-1970s to the late 1990s, we developed a very unique expertise in the use of externally applied post-tensioning tendons to strengthen buildings. In that time period, we completed 110 repair projects using externally applied post-tensioning tendons. Our first repair project using external tendons was done in 1977, and it seemed like we were doing 3 or 4 a year from that point on until we wound down the business in the late 1990s. A significant number of the buildings that we repaired had earthquake damage, so the technique has been used to repair many structures which have been damaged in earthquakes. Notably, after the Northridge earthquake, the big Northridge earthquake in 1994 in Southern California, in the subsequent 3 or 4 years, we used external tendons to remedy and retrofit more than 20 structures in Southern California. The techniques for seismic repairs are very similar, if not identical, to gravity load repairs with external tendons. So basically everything that I'm going to be saying in this talk applies not only to seismic repairs but to gravity load repairs. The typical type of damage that we saw that was caused by earthquakes is this. It was punching shear. The Northridge earthquake had unusually large vertical accelerations, and it did produce damage like this in a large number of two-way slab buildings. So when we were brought in on a building like this to provide retrofit services with external tendons, it's a little bit misleading to say repair because obviously there's a lot of concrete repair that needs to be done, but in most of these buildings it was found in the investigation that the punching shear capacity of the slabs did not satisfy the current code. So the use of external post-tensioning was used to increase the strength of the punching shear section. Every kip that we picked up and put in the column was one kip that did not have to be carried on the critical section. The advantages of external post-tensioning for strengthening are many. Primarily, it's a technique that can apply a very large beneficial load at virtually any point in the structure with minimal headroom. It does that because it uses high-strength steel. The system is substantially weightless. It has no impact on existing columns, footings, or the seismic system. A huge advantage we found over the years is that it can be adjusted to avoid existing mechanical and plumbing systems, HVAC and mechanical systems, and it rarely, if ever, requires any changes to the existing systems, and building owners just loved that. And finally, another thing that was very advantageous is that the system can be installed without disrupting the building function. You normally do not have to shut down a building to apply an external tendon retrofit. Now, occasionally we would have to block off one or two parking stalls, but that would only be for a couple of hours. And again, in a number of these buildings, we did our work at night and did not involve disruption of the existing facility. The basics of a typical external post-tensioning retrofit can be described here. It's kind of analogous to building a king post truss into the structure. The lower cord, the tension cord of the truss, is the stressed post-tensioning tendon. The king post is a structural steel assembly that applies the upward load. We used to call this a saddle. I noticed that it's called a deviator now very commonly. We used a structural steel tube that had a bearing plate which was bolted to the existing structure. We welded a double extra strong steel pipe to the bottom of the tube under which the tendons passed. We called that pipe a roller. It didn't roll. It was welded to the tube, but we did use that terminology, roller. The existing structure then becomes the compression cord, the upper cord of the truss. We would drill holes through the existing supports, either columns or walls, attach anchorages and bearing plates, and when everything was installed, we would stress the tendons. They would try to straighten out. They couldn't straighten out because they had this big structural steel deviator, and that, when things came to equilibrium, we applied a very significant upward beneficial force to the structure. The reactions to that upward load were carried directly into the existing supports and did not change any axial load in the structure. The efficacy of an external post-tensioning system is dependent on the amount of available sag that you have, and that is a function of obviously of headroom in the existing structure. The one thing that can eliminate the use or prohibit the use of an external tendon system is limited headroom. We've strengthened all types of existing framing systems. That would include one-way slabs, where we drill holes through the existing beams and build a truss at some convenient spacing, like about 6 feet on center, into the slide. We've strengthened beams and girders. That typically involves wrapping a structural steel kind of saddle assembly. Normally, we didn't have a lot of headroom available below an existing beam, so we would solve that by wrapping a relatively thin plate around the soffit of the beam and with structural steel tabs on the side, and we would weld our pipe, our roller, to that, and that took the upward force from the tendons. At the existing supports, we would drill holes through the existing member, and typically we would insert a double extra strong pipe through that hole because we thought it gave better bearing when it was dry packed, and we applied the tendon force to those tubes or those pipes. Of all the 100-plus buildings that were repaired, I would say 75% of them were two-way slabs for one reason or another, either a strength deficiency or excessive deflection. It's a little tricky because the most beneficial place to apply the upward load in a two-way slab, in plan is right in the middle. You get the most bang for your dollar, if you apply the load right in the middle. That relieves, for every kip of upward load, that relieves the most deflection and it relieves the most bending. It doesn't relieve the most shear, but most of our repairs, except for seismic repairs, were flexural repairs. Now, the most direct way to apply that load is to run the truss diagonally between two columns, dumping the load directly between two columns. But we found that was rarely possible for two reasons. Most of the columns that we encountered were either square or rectangular, and that shape just doesn't work with drilling through. Plus, the orientation of the column bars virtually never allows you a clear path through the column, and then there's the problem of bearing plates on the outside at that corner. So we developed a system for two-way slabs using orthogonal trusses, where we would apply the upward load here at the center of the slab, and we would do that with what we called a beam truss that ran parallel between columns, and it carried its load over to what we called a girder truss. It dumped its load down. It was the beam truss was low here, of course, and high here. It would dump its load down onto another type of saddle that we called a B saddle, that had a roller at the top oriented to take the beam truss, and then another roller at the bottom that would take the girder truss, which would carry the load to the columns. And we probably did 70 or 80 buildings with this method of orthogonal trusses. Here's what one of those orthogonal truss systems looks like in a building that we did repair. This, by the way, this photo was taken after the fireproofing was applied, and I'll talk about fireproofing in a minute. But this is the A saddle. This is where the upward load is applied to the center of the panel, and this is the beam truss, and it carries its load over to the girder line where it dumps its load down on what we called the B saddle that had a roller at the bottom that could accommodate the girder truss, which carried the load over to the columns. It was a little tricky. You had to be very careful that the upward load was bigger than the downward load, or some very strange things would happen, and did happen occasionally. But that's what the orthogonal truss system looked like. This is in an office building that we did in the late 1980s. It will eventually receive a suspended ceiling. This is the only one of our 100-plus buildings that we repaired using external tendons that did not apply an upward load on the structure. The beneficial load in this building was applied horizontally. It's an interesting building. It's a landmark building in Southern California. It's the Orange County Hall of Administration. It's the center of government for a very large county, Orange County in Southern California. It contains many of the county offices. It contains the meeting hall for the Board of Supervisors, where all the important laws are made in Orange County. And obviously from the architecture, it's a very, very focal and public building. You notice that the columns slope outward. On all of the exterior columns slope outward to allow the floors to get bigger as you go up the building. In one, perhaps the most amazing engineering mistake I have ever seen in my career, the horizontal tension load that is required or that is exerted into the floor system that prevents the columns from rotating outward was ignored in the design of this building. The columns were designed for eccentricity of the vertical load, but the horizontal load that prevents the columns from rotating never appeared in the calculations anywhere. The building was built in about 1980, and a few years after it was built, there was a moderate seismic event in Orange County, about a 5.0. And it moved things around in the building enough to where the county hired a structural engineering firm to inspect and investigate the building and to recommend any repairs. In the course of the investigation, this engineering firm noticed at every single exterior column a very noticeable line of circular cracks that was forming around in the floor slab around every single column. In other words, the columns were literally ripping out of the floor slab. No one knows how badly that was aggravated by the earthquake, but it obviously didn't help. And that certainly got everybody's attention, this crack pattern and the fact that people could physically see what was going on. It would ruin everybody's weekend if one of these columns rotated out and fell on the street. The structural engineer doing the repair was familiar with us. They knew we had expertise in external post-tensioning, and they also saw that external post-tensioning would be a good remedy for this building. So they brought us in, and we worked with them on kind of an emergency basis to develop a repair plan that simply involved running horizontal tendons across the entire building from column to column and tying the columns together. We established a guaranteed maximum price for doing the work. The structural engineer passed this on to the county administrators, and they were in the process of executing a contract with us when somebody noticed something very serious, that the county, like most public agencies, has laws that require competitive bidding on construction projects. So everything came to a screeching halt. The structural engineer strongly objected, said that he did not want to be involved in a design bid build project on a sensitive repair, which was very specialized like this, and insisted that the county negotiate the contract with our firm, knowing that we had the expertise to do this. So it was amazing watching the decision making. That when you work in a building like this, you sure don't want the low bidder doing this type of work. So in the first time in the history of Orange County, the Board of Supervisors passed a law that waived the competitive bidding process and allowed the county to enter into a contract, a negotiated contract with us. The project was very successful, was completed in time. As I recall, there were 6 strands. We needed about 150 kips of force at each column. In this project, we did that with a very thick steel bearing plate on the exterior of each column location, and we actually had the tapered holes milled into the bearing plate, so we didn't need any anchorage portion that extended out from the face of the bearing plate. And eventually these were covered with little architectural blobs of concrete. Many of our projects required fireproofing. Those were ones where the external tendon system provided a substantial portion of the capacity of the existing structure. And over the years, we tried various types of fireproofing, spray-on like they do in structural steel. We tried encasing the tendons in drywall. But we never came up with anything that was more effective than using a self-furring metal lath we wrapped around the tendons and the structural steel hardware, and we hand-applied a vermiculite plaster. It's kind of primitive, but we never, over all the 23 years that we've done this work, we never found anything that was better than that. We justified it with fireproofing protection tables that have been in the Uniform Building Code for decades and now appear in the International Building Code in Table 720.1 parenthesis 1. The specific section that we use is 1.6.2, where we're told that to protect steel columns and all members of primary trusses, you can apply a perlite or vermiculite gypsum plaster over self-furring metal lath wrapped directly around the column. This was actually suggested to us by a building official in Los Angeles, and we have used it on many of our projects. The code requires a certain thickness of cover for each fire rating. For 2 hours, it requires 1 inch. For 3 hours, it requires 1 3/8 inches. For 4 hours, it requires 1 3/4 inches. We would typically specify 2 inches of cover to get the equivalent of a 5-hour rating, and we did that partly for conservatism, but partly to address the occasional question that came up from a building official about the fact that this table is for structural steel, and the steel that some of the steel that you're protecting here is high-strength pre-stressing steel, and we were always able to satisfy that concern with the fact that we were providing much more than the upper 4-hour rating in the table. One nice thing about the use of the plaster for the fireproofing, again, in most of our buildings, the tendon system was not visible. It was above a suspended ceiling or hidden. And in other cases, the owner just didn't care that it wasn't less attractive than the other stuff that was the plumbing and the other stuff that the tendons were mingled with. But in certain cases like this one, the owner was concerned with the aesthetics. I don't quite know why with these pipes and this plumbing, but the owner did want kind of an aesthetic appearance, so we were able to shape the plaster and get a nice rhombus shape on the saddle. This is an earthquake repair, by the way. This building suffered extreme punching shear distress in the earthquake, and we were able to, and it also didn't satisfy the code as designed. We were able to remedy that with applying these upward loads not at the middle of the panel, but right on the column line to maximize the amount of shear that we were relieving. If you only need 1 or 2 strands, and by the way, all of our work was done with single strand, half-inch diameter, 270 KSI strand that was greased and wrapped, a typical unbonded tendon. Whether it was fire protected or not, we always used individual greased and wrapped half-inch diameter strands. If we only needed to pass 1 or 2 through a hole, you could do that hole with a ROTO-HAMMER. But in most cases where we needed 2 or 3 or 4-inch diameter holes, we had to use regular core drilling equipment with diamond bits. The tendons were stressed with conventional stressing equipment. In many of the buildings that we repaired, we had no access to the outside of the building. That we had no way to stress the tendons from the exterior. So we developed methods for interior stressing, internal stressing. The typical one that we used was a double extra strong steel pipe where we just overlapped the strand at the center of the structure and stressed each strand in each particular direction. It involved some rather careful coordination of getting the forces equalized on both sides, but it was an effective method of allowing us to stress all of the tendons from the inside of the structure. This is a tight view of one of our A saddles, a little short one that was used in a one-way slab repair. It's got a bearing plate which temporarily bolts to the slab just to hold the weight of the assembly. It's got typically a 4-inch square structural steel tube. It has a double extra strong pipe that we called the roller, and we always welded a little tab on both sides to prevent the strand from accidentally rolling off of the roller. This is the B saddle where the downward reaction from the beam truss is applied at the top of the girder, and the girder truss, which carries the load to the columns, is at the bottom under a roller. Here's a typical finished one-way slab repair. Actually, this is a very recent job. I seem to have passed my defective gene for external post-tensioning on to my son, who is a structural engineer and a contractor and has carried on the tradition of doing external tendon repair work, and this is one of his jobs, actually. Here's one of the oldest jobs. This has been in place for almost 30 years now. This is at the Anaheim Hilton in Anaheim, California. It's directly across the street from Disneyland. So if you're visiting Disneyland, you should stop by and see this. It's still there. It was not fireproof. It was a deflection control. There was terrible deflection in these slabs, and we picked up some of these slabs up to 4 inches with this system. It's a two-way orthogonal repair. This is the A saddle right in the middle of the bay, carries its load over to the B saddle, which is here, which carries its load to the columns. So again, that's one of our oldest repairs. It's kind of an unusual one here. This was a girder that we were asked to strengthen. We had plenty of headroom below the girder, and we had access to each end of the tendon, so we were able to drill the holes directly through the end of the tendon at an angle and build the king post trusses under the girder instead of alongside the girder. So anything's possible. We also did, as you can see, a slab repair or strengthening. To summarize, the use of externally applied post-tensioning is a very powerful method for strengthening existing buildings. It has been used to remedy design errors where it increases the flexure and shear strength. It has been used for occupancy changes where nothing is wrong with the building. There's an occupancy change which requires an increased live load. We've increased the live load on a number of buildings from 50 to 100 pounds per square foot. And it's also been used to remedy damage in existing buildings, and that damage has been due to corrosion and seismic damage. Again, it's weightless. It involves no disruption to existing facilities, and it can be generally executed while the building remains in service. There's one other, probably the most important advantage that I haven't listed, and that is that it's very economical. In many of these projects that we've been involved, we have competed on a design-build basis with all other types of repair systems, and we have never lost one of those design-build competitions. So I sure appreciate the opportunity to talk with you today. I think we're in pretty good shape.